what do I need to click?
Oh, Linda's
Got it.
computer
Okay.
is complaining.
No, it's just it's being, they let you know.
You know, with us both being on Zoom, even if you had like an internet outage or something like that, you can just reboot your computer and come back on. You know, running the broadcast, I have lost internet completely, and Zoom keeps the meeting going, broadcasting even. You know.
Oh, that's great.
Isn't that great?
That's nice.
So I can come back in, you know, and
yeah, that's nice. Yeah, if you're the host, on some other platforms, if you're the host and you disappear, the meeting disappears.
It's gone. Exactly. So I've been reluctant to look at other platforms because of that. Just really good luck with that. So
yeah, and Zoom, you can record it, and there's a lot of nice features.
yeah.
How to show tovarish.
That's a cool.
That looks like cells merging and dividing.
It's gone. Okay. And we already have people chatting now. Just so that you know, we have live chats coming in. Okay, and when I feel that it's an appropriate time, I'll ask you questions. You know, I think that's what makes these kinds of programs different from like video broadcasting or something like that. You actually get to interact with the people presenting.
Right. Yeah. If you can see the questions in the chat box. Yeah.
Yeah. And I belong to a lot of groups in social media, so I'm just now sharing.
That was a cool simulation because you could see it hitting the termination shock and compressing the waves.
Yeah, thank you, NASA.
Watch this. It expands it out and goes to a cross section. You see the waves going out and hitting the termination shock here.
Yep. Yep. You can see where the front, the nose is.
And where they get compressed. And you can see the effect of turbulence outside it. Very cool.
We have Pekka Hautala from Stockholm, Sweden watching right now. He says, good afternoon, ladies and gentlemen. So excited about this special that it has about one of the most spectacular moments and happening in space exploration. It's nice, Pekka. Thank you.
Yes.
We have Tarek watching from the UAE. We get a international following of people watching, which is cool.
Just be sure to let them know that we appreciate their interest and enthusiasm.
Well, they can hear you right now, so.
Oh, okay.
Our mics are hot, so.
Okay.
I should have mentioned that too, but yeah. One of the followers' handle is called Bergman Scooter. He says, we're all ears.
Great.
I'll stop short of saying we're all mouth. No, it's really great to be able to share this with an audience around the world.
Yeah, it's amazing the technology we have do this, you know. But I know you're gonna, once we get into all the stuff that's going on in your lives, you're gonna blow their minds. So. A couple of nice women in science groups that we're going to share with.
See that turbulence effect?
Yeah,
out there.
Cool. Yeah.
Hello, everybody. This is Scott Roberts with Explore Scientific and the Explore Alliance, and it's my pleasure to bring you our special program of Explore Now with Tom and Linda Spilker. They have spent a lifetime of being involved in space exploration, planetary exploration. Tom has gone on from the Voyager mission, of which they were both on in the early years of the project, to being involved as a mission architect and a consultant for many space exploration firms around the world, including the Gateway project with a rotating space station that will be built, I guess, within the next decade. So I was talking with Tom about this a little bit earlier, and this space station is like the space station of my, sci-fi dreams. It's just an amazing looking piece of well, not a piece of hardware. This entire living environment. It's going to be in space, and it's going to be very cool. Linda Spilker and I have known each other for about 10 years or so. She has done lectures for the Starlight Festival that we conducted at Yerkes Observatory. She has been interviewed in Skies Up magazine with us, and she's given more than a couple of lectures for our audience, and including she let me come into mission control of the Jet Propulsion Laboratory, which was totally cool for me. I was so nervous, but both Tom and Linda are wonderful, warm people. They are, vibrant and so interested in what's going on in space exploration. And we decided to get together on the anniversary of the Voyager 2 flyby of Saturn, which happened in 81. Is that right?
Right. 1981.
Okay. So
August 25th.
August 25th. So I thought it was awesome that they could come on, both of them, for this, because they were both there. So let's turn this over to Tom and Linda and get started here. I haven't done a very good job in really telling you all about them, but you're going to learn more as this hour goes along. So, Tom, Linda,
why don't you start?
Okay. Well, I've worked at the Jet Propulsion Laboratory now for 44 years. In fact, I got my start on the Voyager mission. I was just fresh out of college, looking for a job, came to JPL, and they said, "Do you want to work on the Viking extended mission or this new mission called Voyager?" And I said, "Well, where's Voyager going?" And they said, "Well, Jupiter and Saturn. And if everything goes well, on to Uranus and Neptune." So I said, "Sign me up." And I worked with the infrared team as the go-between between the science team and the JPL flight team, helping them put together all of the kinds of observations they'd like to see. And it was such a privilege to be there through the flybys of Jupiter, Saturn, Uranus, and Neptune. And during the time I was on Voyager, I had a chance to go back to school and actually used Voyager data of Saturn's rings, the rings of Uranus and Neptune, to write my PhD thesis, got my PhD at UCLA. And along came this great opportunity called Cassini. And I said, how would you like to work on this new mission called Cassini to go back and orbit Saturn? And I said, oh, that would be wonderful. Saturn's rings are the best. And you've got this really interesting moon Titan. And so I spent the next 3 decades working on the Cassini mission. And just recently, I've come back to Voyager. So I'm now working with the project scientist, Ed Stone, as his deputy. As Voyager, both spacecraft are now out in the interstellar medium, exploring the space between the stars. And what a great opportunity now to end my career where I started with the Voyager mission.
Yeah, it's like some sort of a movie script or something. You couldn't write this any better. I'm curious. This is a question, I guess, for both of you. You were at the very, very beginning of Voyager, I think, but shortly thereafter. And Linda, you told me that you got to see the liftoff of Voyager 2. What was it like in the early days, being part of the Voyager team?
Well, on Voyager, it was very interesting. The focus up until launch was really building the spacecraft, building the instruments, and getting it all buttoned up and sent down to the Cape. Mm-hmm. And they hired a group of us, a bunch of actually 20-somethings, a lot of us fresh out of college, because now you needed a team to help run the spacecraft, operate it, to point the platform, to look at your various targets. And so I joke with some of my colleagues and I say they gave the keys to the spacecraft to a group of 20-somethings. You then take that spacecraft and fly it past all of these worlds. And it was really a very exciting and very interesting time. We weren't sure exactly what to expect because really, if you thought about all the moons of these places, they were pretty much just, tiny dots in a telescope, especially when you got out to Uranus and Neptune. So a chance to go and explore in some of these places for the first time, that was just tremendously exciting. And that you could feel that excitement bubbling along at JPL as we planned all of the sequences. And just kind of for context, when we first started, when we drew out the timelines, what we do each day, we basically took a ruler and a pencil and a long sheet of vellum paper and actually drew them out. And of course, by the end of the mission, that was all computerized and it was very different. And to run any of the programs took boxes of those old computer cards, and you could see people carrying them around for the trajectory or whatever, and going to the computer with their deck of computer cards. So such changes now.
Right. So, just as a young student watching, Voyager take off and the hope and the, the whole project seems so fantastical. Here we are going to the outer planets, the images that came back of the, Jupiter and Saturn and its rings. And it was like discovery after discovery, I guess with gaps, as we're going to the next planet. But, everybody was like on pins and needles as we would hear about these flybys that were going to happen, and I can't imagine what it was like to be in the driver's seat of all of this.
And Scott, that excitement is actually what got me into my current profession. At the time of Voyager's launch and the first Jupiter flyby, I was an exploration geophysicist, and that Jupiter flyby reminded me I'm not supposed to be looking this way. I'm supposed to be looking that way. And at that point, I made my plans to go back to school, and that wound up with me getting my PhD at Stanford and going to JPL.
Wow. And that's where you two met, of course. And I guess the rest is history.
Right. Well, Scott, it's really interesting. I was at the Voyager launch and everything appeared to go perfectly.
Yeah.
But that first launch of Voyager 2, the spacecraft got up there, and I think the vibration was a little bit more than it was expecting. And so the spacecraft started swapping between its various computers and pieces of hardware. And it was like Voyager was on mutiny. It wasn't sure what to do. And so it took a while, but finally, one of the people who helped write the software and understood the spacecraft said, let's just give it some time. Voyager will settle down and it'll be fine. And so that's exactly what happened. Voyager 1 launched actually a little bit later, but actually then on a faster trajectory, passing Voyager 2. But in that case, it turns out that the first one of the rockets, the second stage, had started to underburn. And it turns out we had to burn that second stage longer. And I think we only had like 30 seconds of propellant left. And so Voyager 1 almost didn't make it.
Oh my goodness.
Charlie Cole Hayes said when that second stage, that final stage finally shut down, they had 3 seconds of propellant left.
So both of them had exciting.
He had no fingernails left. Oh my gosh. So that was certainly a close call. Have there been others that you can think of? I mean, there was a situation with one of the instruments have failed as the spacecraft has aged, but we're still talking to it. We're still getting data, so.
That's right. 21 hours at the speed of light to get a signal from Voyager 1 back to the Earth. Voyager 1 is almost 150 AU, astronomical units away, and it's just getting further every year. And Voyager 2 isn't far behind. So it's just amazing. The furthest man-made objects that we have from our sun. Right.
Do you think, I mean, this is on this anniversary, this particular, the Voyager 2 flyby of Saturn, was that a special moment for you and Tom, or was that like, okay, I mean, you're both very, you're professional scientists and everything. Was there a lot of emotion involved in that, or it was just kind of like, yeah, this is data. We're getting more data here. I love it. But, how was it for you guys?
I think tremendous excitement. I remember watching those images come back, and I'd sit there and watch. They had monitors all around the area where I worked, and I'd watch line by line as each of those pictures came back, wondering what would I see that might be new and might be different. And of course, we'd had the Voyager 1 flyby 10 months earlier. And so in some cases, we had a chance now to more carefully observe, for instance, the rings. We looked for moons in some of the gaps in the Cassini division, and to sort of follow up on some of the Voyager 1 discoveries. But Voyager 2, it was almost kind of a bittersweet time because we knew it'd be 5 more years before we'd get everyone together with the press and the scientists all together at JPL. And that was for the Uranus flyby. So we were looking at a period of time where we'd have to wait until we had the next flyby, because it had just been boom, 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 2 flybys in 1979 of Jupiter, and then 1980 Saturn, 1981 Saturn. And that was like, oh, wow, we've got to wait 5 years for our next flyby. And for Voyager 2, everything looked like it was working like clockwork. We went behind Saturn, the closest point we approached Saturn, and Voyager came back out, and we noticed that many of the pictures were just dark sky. And it suddenly occurred that the Voyager scan platform had gotten stuck. We had used it so much going from moon to moon and back to the rings and the planet that we had just literally squeezed the lubricant out, and the scan platform stopped working. And we did get it fixed ultimately, but oh boy, there were a couple of days that we were wondering, as we slowly tried to get it to move again and go back and at least look at Saturn outbound. And I remember I was telling you, Scott, earlier that one of the things we were planning to do after that closest approach was to get some of our highest resolution pictures of Saturn's moon Enceladus.
Right.
And it was going to be at high phase angle where the tiny particles would really show up. And I always wonder, would we have seen that plume of icy material coming out of Enceladus's south pole? Because at the time of the Voyager flybys, the Enceladus south pole was dark. It was winter at the South Pole, and we didn't see the tiger stripes, and we didn't know about the plume coming out of the South Pole. So I look back and I think, well, maybe Voyager left a discovery for Cassini, left a gift, something for Cassini to
Oh,
discover.
yeah. In
on his
retrospect,
mission.
right? But
In
you didn't know
retrospect,
yet that you would be
had
on
no
this.
clue, had no clue. Had we known, I wonder too how we might have changed the Cassini instruments if we knew there was this plume of material at the
Right.
South Pole.
Yeah,
So,
you might have developed some special instruments just for that.
I was with the radio science team, and ours was also one of excitement, but also anticipation with a little bit of trepidation, because we didn't have an indication ahead of time that the radio science experiment was working properly. The only thing that happens is when it first goes behind the rings as seen from Earth, you should see the radio signal strength drop all of a sudden. So we were there watching the monitors and, oh, I hope this works right. And suddenly when you see the signal strength along the plot go down and back up, oh, there's the F ring, we got it.
That's cool. That is cool. So during this early phase, the team consists, of course, of you two. Ed Stone is there. Carl Sagan, is he?
yes,
there?
yes,
Is
Carl, yes, he was there, and he had his Cosmos series going at the time. And yes, he was a very important part. He worked with the imaging team.
I see.
And looking at their data.
And hundreds of unsung heroes in the engineers and scientists that did all the planning and the engineering of the spacecraft and the engineering of the sequences that ran the spacecraft and so on. And Carl Sagan himself said the names of those engineers should be known worldwide.
Right. Yeah.
Yeah,
Yeah, they
there were
should.
11 science instruments on board Voyager, and each of those was led by a principal investigator. And the project scientist, Ed Stone, actually had an instrument, the cosmic ray spectrometer, on board each of the Voyager spacecraft.
Wonderful. Wonderful. And Ed is still with the project today?
Ed is still the project scientist. He started when the mission was just in its infancy, when the spacecraft and instruments were being built, and he is still, I'm sure, will be with the mission till its end.
Yeah, I certainly hope so. I hope so. So this team that's now the Voyager project team, is it many people that are very experienced like yourselves, or is it also some young people that are just starting out?
The Voyager team, for the flight team, really consists of a lot of the engineers that helped put Voyager together and helped fly Voyager. So a lot of them have come back.
Oh,
It's
wow.
a very small flight team. It's about 15 people. And we're in the process of training up now other individuals as well, because we're finding that people are retiring. It gets to that time and they're retiring. And so the project manager, Susie Dodd, says, one of our most important lists is the emails for the retirees so that we can keep in touch with them if something happens with the spacecraft. Many of the principal investigators are the same as the ones with which Voyager launched. And we've brought in a team of guest investigators, young scientists, to basically hand over the knowledge and how to process and look at the data coming back from Voyager today. And they're an integral part of the science steering group meetings and give presentations and are making discoveries of their own now with the Voyager data. And that's cool to see.
Yeah. Pekka is commenting right now from Stockholm. He says, this is so much better than Discovery Science broadcasts. To see these Tom and Linda talk up to us directly and tell us things in detail, that's not in the documentaries. Wow. That's true. That's why we do these, Pekka.
Well, in addition to getting the lists of the retirees, one of the things Susie did was go around JPL and round up all the 30-year-old computers that could still run the software that was written for Voyager.
Yeah,
they should be in a museum someplace or preserved somehow, That's fantastic. It really is. Let's go back a little bit to the Golden Record. Some of the things that wasn't, I guess, considered hard science. I'm putting sounds of Earth and
pictures and
these things. That's kind of humanitarian somehow our something about our humanity. And then the pale blue dot, what kind of pushback was there, or was there any? I mean, did the team embrace these kinds of ideas for Voyager, or was there pushback, like saying, hey, we're not going to turn Voyager around to take a picture of the Earth, it'll just be on a pixel or two,
Yeah.
I'm curious about that.
There was some pushback in that we had to wait until we were past Neptune before we could turn the cameras back, because we knew we'd be taking the cameras very close to the sun. And so there was some risk of getting very close to the sun. And it did take some convincing, and Carl Sagan was very good at that, and convinced the team that it would really, really be fantastic to look back at our solar system and basically take a series of images that included each of the planets, including the Earth. And the story about the picture of the Earth, the pale blue dot, as Carl Sagan calls it, was a friend of mine, Candy Hansen, had put together the sequence, and she said she was looking through the images and noticed a lot of scattered light from the internal optics of the camera. And so the Earth image had a lot of scattered light. She was looking at it, and she noticed this dot in a sunbeam. And that dot turned out to be just where you'd expect to see the Earth. So here's the Earth in a sunbeam, our pale blue dot, looking so tiny against the backdrop of space.
Amateur astronomers read Pale Blue Dot by Carl Sagan again and again. There was about 2 months that I just made myself read it. First thing upon waking was the pale blue dot, just because of the perspective that it gave us, but that's just the door that opens about this, of the exploration, discovery, it's just never ending, and I think that there's a lot of people alive today that might have heard about the Voyager project, but don't think it's an ongoing project. This happened a long time ago, right? So, but that exploration and discovery is still going on. And both of you, having grown up through this and being involved in these projects together, and now, doing different projects in the ways that you guys do them, I can't even imagine what it would be like what would be in my mind is Tom and Linda Spilker thinking about, if I look up at the sky and what that's like, We often talk on our program called Global Star Party about the feeling of this, and how it's changed our lives. And, we don't have the perspective and knowledge that you two do, but it is life-changing. And so I think that you guys do incredibly, very important work for all humanity. I really do. So
thank you, Scott. One of the ways I like to look at it, and this is not just Linda and I and our colleagues, it's everybody that goes out and makes it a point to look up at the sky and not just see some light coming down from the sky, but understands what they're looking at, maybe does some research, reads, or gets out a telescope and looks at what they're seeing in the sky. It makes the difference from being just a casual observer of the universe and being a participant in the universe. That involvement and that understanding makes you an active participant, and that just opens up so many avenues and contributes to this feeling of, hey, I'm part of this. I'm not just watching it, I'm in it.
I'm in it. That's right. That's right. Wonderful. Linda, you showed me a number of slides earlier. Did you want to run through some of your?
Sure. I put together sort of just a very brief overview of some of the things that we've done with Voyager.
Okay.
Let's see. I think I need to go back to the beginning quickly. Okay, this is a slide that's showing the Voyager instruments, indicating where they are. The instrument that I worked on was on the little platform that's over on the right.
Mm-hmm.
let's see if you can see my cursor. The
Yeah.
scan platform had the cameras, the infrared and UV spectrometers, and the photopolarimeter, and then a whole suite of other instruments to measure the particles and fields. And then actually the high gain antenna itself is what we used for the radio science experiment. So I need to put a label on there to indicate that there's our 11th instrument.
And that was my instrument.
Oh, that's cool.
And this little gold circle in the middle of the bus that we call for Voyager, that's the gold record. And there's a cover on top of it. And the cover shows a diagram of the size of a man and a woman next to the Voyager spacecraft. There are diagrams and information about where we're located, using quasars and various things. And also we included a stylus to play the record and showed them that the first image should be a circle. And once you get that circle, then the rest of the images would follow.
Wow.
And this is one of my favorite pictures, in commemorating the Voyager 2 Saturn anniversary. This is the Saturn family portrait. And so you see Saturn and a number of its moons. We didn't take this picture, but it's made up of pictures of the different moons that we took. One of those was Titan, and Titan was a target of interest, especially for Voyager 1. And Titan is a moon with a thick nitrogen atmosphere. And we were hoping to see through the clouds to the surface, but unfortunately we did not. But fortunately for Cassini, the fact that we couldn't see through that haze and the clouds then led to the Cassini mission, and we carried a probe called Huygens, which we parachuted down to the surface of Titan. So just a few highlights. This is Jupiter with the great red spot, that great storm, 2 of its moons. This sort of yellow reddish one is Io. The other moon is Europa. And we found that Io had active volcanoes. These are just some of the close-up images of those volcanoes. You could actually see lava flowing out onto the surface of Jupiter's moon Io.
It's the most volcanically active body in the solar system.
Yeah.
Yeah, the black and white picture on your right, we, just to be thorough with Voyager 1, we said, well, we know Jupiter doesn't have a ring, but just in case, we'll take this picture. And so what you can see is the squiggly looking brighter white lines are stars. This is a long exposure.
Okay.
So with the limit cycle of the spacecraft, the stars made these wiggly patterns, but we were targeting to this faint ring right here. So in this Voyager 1 image, we knew that Jupiter had a ring. So with Voyager 2, then we set up the cameras to take the picture you see here. And it's a very diffuse ring. It's not like Saturn's rings, but it turns out all the giant planets have ring systems. This is an outbound view of Saturn. We got to see incredible detail, what looked like thousands of individual ringlets around the planet. Voyager discovered spokes. Yes. These dark finger-like projections of dusty material that get elevated above the rings. And they go into the darkness, and we think the dust charges up, and then they come out on the dawn side, and you can actually track these spokes around the planet.
And they change shape, I assume.
Right, they change and they come and go, and some longitudes are more active for spokes than others, and they're in the middle of the B ring, very close to what the synchronous rotation distance would be at Saturn. And here's our best view from Voyager 2 of Enceladus. And we saw a world so different from the other moons. It was bright, white, icy, one of the brightest icy moons in the solar system. You can see places where the craters are very subdued or non-existent, fractures, and we were so intrigued to figure out what had caused this resurfacing on Enceladus. And we now know it's the material from the plume that falls back to the surface and actually is filling in those craters.
Wow.
And then 5 years later, it was worth the wait. First spacecraft to fly by Uranus. Uranus is tipped on its side. And so when Voyager 2 flew by Uranus, we're actually looking at the pole. So there's a true color view on the left, and on the right is a false color view. And you can see the reddish point is where the pole is located. Mm-hmm. Mm-hmm. Here are the rings of Uranus, 9 very narrow rings that we had seen from the Earth in occultation. So here we're getting our first ever pictures up close of those rings. One of those, the outermost ring, the Epsilon ring, in the picture on the right. The little circles indicate 2 tiny moons that we think are part of confining the material in between them, but we didn't see any other moons to help find the other rings. So something else must be going on.
Hmm.
And then of the moons of Uranus, the most interesting, and just fortuitously, the moon we flew closest to was tiny Miranda. And Miranda looks like a world that's been torn apart through some cataclysmic event and then shoved back together. And so it has a very interesting and intricate surface. And so it's one of the major moons closest to the planet. There are other smaller moons as well. And then a series of 4 other moons. Here's Neptune. Neptune has what we call the Great Dark Spot, very reminiscent of Jupiter's Great Red Spot. It's just a huge storm that was swirling around that we observed as we flew by Neptune.
And 5 or 6 years later, that storm had disappeared, and another one a few years later appeared up in the northern hemisphere.
Oh, wow.
Just a fascinating place. Neptune has very faint diffuse rings. So here's a picture of the Neptunian ring system. Neptune would be in the middle, but it's blocked out here. We didn't want to get the light from Neptune.
It looks like it has a complex system like Saturn's rings, you know.
It's more complex, but this very faint and very, very dusty system. Could be that when this next object, Triton, is a captured moon, and it could be that Triton really disrupted the system. There are not many moons left in the Neptune system. As it was captured and its orbit circularized, it probably made some changes in the system. And the neat thing about Triton is you see those dark patches in the light region. Now that's at the pole. And these regions, we actually saw geysers coming up out of these regions.
Oh, wow. Okay.
You know, we wondered to this day, does Triton, like Enceladus and Europa, perhaps have a subsurface global ocean? Yeah. And so we'd like to go back both to Uranus and Neptune, maybe with orbiters like Cassini. And here's that pale blue dot image with the Earth and a sunbeam. Just very, very striking. One of, I think there were about 60 pictures that were taken as part of this series. And where are Voyagers today? Well, they're outside the heliopause, outside the boundary that's controlled by the sun, into the what we call the very local interstellar medium. And so sampling for the first time, basically the wind between the stars. And you can see that bright sort of yellowish region, that's the bow shock region. The Voyagers are headed toward that. We're not sure exactly where that region might fall. And with that, let's ask Tom to say a little bit about that. Was the quick look across the Voyager flyby.
Voyager, yeah.
And now back to Earth.
Look at this thing. This is
the space station, and I want a ticket when it's done. I want to get a ticket.
Me too.
I want to go.
Well, there was a lot for me between Voyager and the station. And actually, we've named it the Voyager station that you're seeing here. I spent after Voyager went by Uranus and Neptune. I had completed my PhD, and I went to JPL for 20 years. Worked on Cassini for a while, worked on the NASA Genesis mission, and worked on ESA's Rosetta mission. So a lot of mission involvement in there. Retired from JPL in 2012 to do independent consulting in mission architecture and planetary science. And then several years ago, got involved with the group that is wanting to take advantage of the coming very much less expensive launch costs for getting things into orbit and out of orbit to build much larger things than we'd been able to build before. When you're paying $10,000 a kilogram to put things in orbit, that really limits how much you can launch. When those costs go down to $100 or $200 per kilogram, or even less than that, a lot of things that you would never think about doing before suddenly become feasible. And this is one of the things that we're thinking about. This station that we're looking at here, and we're expecting to have first rotation, not with all of the 24 modules that you see there, but the first ability to rotate within a decade. The diameter of that from the tip of those what we call emergency return vehicles, they're the equivalent of lifeboats on a cruise ship.
Right.
It's a little more than 100 meters from the center out to the tip. It's about 107 meters. So 214 meters, or something on the order of 700 feet across.
Huge.
Yes. We have 24 of those habitation modules and 44 of the emergency return vehicles. Those are not space shuttles. Right now, what we're saying is that we will use Sierra Space Corporations. They're a spinoff from Sierra Nevada Corporation. They're dream chasers. So you can put 7 people in each one of those. And we're looking at a total passenger and crew complement somewhere between 300 and 400 people on one of these stations. Now you notice it's wheel-like, and that brings you back to 2001: A Space Odyssey.
That's right.
Indeed, it rotates to produce artificial gravity. We just today are submitting a proposal to do a smaller version of this that's a stepping stone to doing this larger station that would also do artificial gravity and be the very first facility in orbit in space that provided any significant level of artificial gravity. So we're very proud of that.
Yeah, this is, as I mentioned earlier in the program, I mean, this is, truly, one of the things that I would think, science fiction becoming science reality, I am very happy to see it come together, and it looks like you and your team are making it happen. So that's amazing. What do you think the overall cost of this project will be?
Oh, for the big one, it would be something on the order of tens of billions of dollars, but it would not be NASA money. This would be completely commercially funded, and that would be for the first one. Once we know how to build the first one and have all of the equipment for building those modules and the pieces in between them we call couplers, the later ones would come much cheaper. And so we'd bring down the cost of going and visiting a place like this orders of magnitude. Right now, to visit the ISS, the International Space Station, the cost for a 1-week stay is, I believe, $55 million. And that doesn't include the taxi ride up there. Right. So you have to contract with somebody to get you up there. And right now, the going price for that is about $20 million. So you're talking about $75 million for a visit. We're talking about, when we first start out, less than 1/10 of that, and eventually 100th of that. And the longer we go, the more things that we build, the less expensive they'll get. The less expensive the launch vehicles get, like when SpaceX's Starship comes online, the less it will cost you to get up there. So eventually we want to have the cost of going up there be something like you'd pay for a vacation from the US to Europe or from the US to Asia or something like that. For the average person, that's a once in a lifetime kind of trip. And we want to give them the option of thinking, okay, for this once in a lifetime trip, do I want to go to Asia or Europe or to space?
Or to space. I know what my answer is. So
me too. Yeah.
Now on this station, we're not rotating up to 1G. If you want 1G, stay on the ground.
Yeah.
So we want people, from the minute they wake up on the station, they know I'm in space. I'm not on the ground. So we would rotate to about a lunar G. And
so
you could literally bounce out of bed in the morning. And because it's rotating, there are all kinds of interesting things that you would notice. For instance, if you held up a pitcher and started pouring into a glass, the stream of water would curve because of the rotation.
Right.
We would have a gymnasium, actually a couple of gymnasiums in 2 of the modules that double as auditoriums. And I did some calculations for new games that could be played in such things that you could not possibly do on Earth. And I calculated that if you can run at 6.1 miles per hour, which is kind of a jog, it's not running very hard. You can run up the wall of a module, around the roof, down the other wall, all the way around. And you have a snail race. The person that can do that the slowest without losing touch with the wall wins.
Right. Yeah. Would a fall hurt you, do you think?
if you did it completely wrong, if you conspired to do the worst fall that you could do, yeah, it might hurt you. But if you were doing this snail race, you'd miss a couple of steps and then probably go rolling around the wall until you get down to the floor.
Right. Wow. This is amazing. Do you think that, well, this thing would have to be inhabited 24/7, I would think.
Oh, yes.
Is this something just for space tourism? Is there a larger purpose of having space stations like these?
This is one of the really good things about having it modular like this. We can have, of the 24 modules, maybe 12 or 14 of them are hotel modules, but other modules can be specialized for research. Some can be specialized such that you have lunar regolith simulant and lunar surface simulant, and you have lunar G. So if somebody builds a machine that they want to take to the moon and use it on the moon, which NASA and other entities are talking about doing in the future, you could take that machine up here and test it under actual moon conditions without having to carry it all the way to the moon to test it.
Right. Right.
There are many different applications that you could do, and you can specialize the different modules for doing those applications.
Now, building out this space station, I can, I envision, 1,000 astronauts out there working, bolting it together. How will it get built?
Well, we actually will be building machines. And the station, the precursor station that we just proposed, is developing some of these machines. We'll have machines on the ground that build the entire modules and entire couplers, and you launch those as one piece. So they get up there and you have robotic machines that are attached to the truss, the ring that goes around just inside those modules. There's a robotic system that actually builds that truss. And then there's a robotic system within that truss that can take a module that's being delivered by a spacecraft, put it on essentially an arm, and locate that module there on the truss for attachment. And the attachment itself would be done robotically also. Oh, so wow. The great majority of the assembly is done robotically, mainly to save money. The cost of having an astronaut do a job is orders of magnitude per hour higher than having a robot do it. So rather than having astronauts and people who would have to be very highly trained and expensive in orbit doing these fairly mundane tasks like driving bolts and so on, we'd have automatic systems to do that.
Wow, amazing. Folks, you're seeing the future here unfold. It's really cool. Here's a comment from Tarek and in the UAE. He says, we're watching Spilker and we can feel their time back as if we were with them. It's nice to hear all their astro journeys and experiences around the world. This is very nice.
Thank you.
Yeah. Let's see. Cameron Gillis is commenting on the pale blue dot, saying absolutely amazing and profound image. There
was a very nice quotation from Carl Sagan about that pale blue dot when it was shown to the public. And I will shorten this, but he said, everybody you've ever known, everybody you've loved, everybody that ever existed on that little dot.
That's true. Yeah. He talks about the rivers of blood that were spilled and, the self-importance that people have and stuff. And, I think this space station will give people the, that overview effect that astronauts have experienced. I think that is something that will change humanity more and more.
One of the things that we're hoping to do with this station is we've had lots and lots of experience with humans in 1G. We know exactly how humans behave in 1G. We've had thousands, maybe even now millions of human hours at 0G, and we know how nasty 0G is on humans.
Mm-hmm.
Where in between there is the threshold where this decreased amount of G no longer causes eventually fatal problems in a person exposed for a long time to that kind of environment. So this kind of station would allow the research to do exactly that. Figure out how much G do you need to prevent loss of bone? How much G do you need to prevent loss of muscle mass? How much G prevents the loss of visual acuity and brain function? It may be different levels of G for each one, and it may be that the level that you need for one is not enough for the other, but that level of G plus some pharmaceuticals or exercises or something is sufficient. So it allows you to do that kind of research to figure out if we're going to go out in space, somebody's going to be in a spacecraft for 5 years or 10 years or something like that.
Right.
What level of G do we need to supply to make them able to live for that long, and not just live, but thrive and function well and do the jobs that they're supposed to do?
Right. Maybe live even better than they do on Earth.
Possibly.
Could be, yeah.
Tarek is asking, he says, my question is, why did they call the Voyager mission Voyager? And whose idea was it for launching it?
That's a good question. I'm not sure where the name Voyager came. It was originally Mariner, Jupiter, Saturn, and then they had to come up with a name. And actually, the original idea for Voyager goes back, it would have had at least twice as many spacecraft and would have included trips to Pluto as well. And when looking at the budget constraints, et cetera, then it was when we got down to 2 spacecraft, the original purpose was Jupiter and Saturn, but the navigators were very clever in finding a way. The planets were lined up in just the right way that you could slingshot yourself from Jupiter to Saturn to Uranus to Neptune, and then out of the solar system.
And it turns out the original idea for that kind of mission, that slingshots to Uranus and Neptune and various variants on that, came out of a fellow who was doing research into trajectories. I believe he was at Purdue University.
Could be.
Anyway, this graduate student was looking at various trajectories in the solar system and found this trajectory that requires a particular alignment of the planets that only occurs every 176 years.
Oh my gosh.
And he said, if you launch in 1977, you can go to, in order, Jupiter, Saturn, Uranus, and Neptune. And that idea started percolating around, and people started thinking, how can we use that? We have enough time to respond. How can we use that?
Wow. So this was already decided. This path was already decided before they launched, I would imagine. It wasn't like something like, oh, by the way, we can do this, right?
Right. Well, actually, it turns out the focus at Saturn was Titan. And it turns out that had Voyager 1 malfunctioned or not gotten the necessary information on Titan, then Voyager 2 could have been programmed to follow the same trajectory as Voyager 1, which would have taken it out of the ecliptic and away from the possibility of Uranus and Neptune flyby. But Voyager 1 got back all the data that were needed. The mission was very successful for that flyby. And so that allowed the navigators then to plot the course, where we would fly by and how we would fly by Saturn to go on to Uranus and Neptune.
And the spacecraft engineers very nicely said, okay, we're going to engineer the spacecraft to do the prime mission through Saturn, but we will do nothing that would preclude going on to Uranus and Neptune. So the spacecraft was designed so that, yes, you could do that. It focused on Jupiter and Saturn for the prime mission, but they made sure to design the spacecraft so that nothing about it would preclude going on to Uranus and Neptune.
And as we went further from the sun, we had to make changes in how we would take images, because then smear becomes a problem. The exposures get longer, and it just allowed those engineers to get even more clever to actually start to turn the whole spacecraft at just the rate you needed to keep the smear out of those pictures. And it was just really incredible. And of course, the data rate went down. You're further from the Earth. And so it took longer to send back each picture. So at Jupiter, every couple of minutes, you got a new picture. And by the time you got out to Neptune, you were now waiting 5-6 minutes between pictures.
And that was 5-6 minutes with multiple big antennas put together, all listening at the same time to put their signals together to increase the data rate as much as possible. So it was 5 or 6 minutes instead of an hour.
Right. Amazing. Amazing.
And now the two Voyagers, the return of data, it's at 160 bits per second. So
That's
it's
it?
very much slower than the data rates that we had for those planetary flybys. It takes a long time. And one of the tape recorders is still working on Voyager 1. And instead of putting images on that tape recorder, we put plasma wave spectra, basically the radio waves that it's sensing from the interstellar medium. And it was so clever, written just like the lines of an image, played back just like an image. And so when we play back that tape recorder, we have to take a big 70 meter and all 34 meters at that complex, all working together like one giant ear to listen for that playback of the data. And that happens about once a quarter. So 4 times a year, we have to find all the stations, put them together, and play back the data.
Amazing. Amazing. I remember going when I was walking into where the Mission Control Center is, and there's like this pillar that all these lights are running down. And I thought it was just kind of this cool artistic visualization, but it actually is showing real data coming down. Is that correct?
That's right. That's right. It basically shows the uplink of the data to the spacecraft, and then when it comes back down, and in fact, if you're getting
it's moving the other way
from a Mars mission, it's coming down really fast. It's like a heavy rain, and then you get a playback from Voyager, and you see it's like a sprinkle in comparison at the rate at which the data comes back.
Wow. I mean, it looks like a prop from, Star Trek or something, it's just so cool.
Great visual,
Very visual. And then when you go into Mission Control, you see there's like a glass plate in the floor. And I forget what it says, but there's like a plaque down there.
Center of the universe.
Right. And this place is so historic. I believe one of the stories told to me is that the Apollo 11 live televised images of Neil Armstrong stepping on the surface actually came through that particular Mission Control Center. Is that true?
Yeah, I don't know if that's true.
You don't know that's true. Okay. All right. Well, we'll save that one. Our last global star party, which was Tuesday night, the theme of it was ringed planets. Okay.
Oh,
and
cool.
So it's wonderful to have you two on here. I think possibly Linda knows more about ringed planets than anybody alive. Okay. So it's, and what a great thing to study. I did not know that, that some early astronomers using, I think people like Herschel and some of these other people thought that they had detected rings around some of these planets that we didn't confirm, until Voyager. So that is it's interesting from that perspective. But and then there's exoplanet, at least one exoplanet that's determined to have some rings or a lot of rings. So.
And now we know that you don't have to be a planet to have a ring. We've got at least 2 asteroid-sized objects, Chariklo and Chiron, that appear to have ring systems around them.
Isn't that amazing? Yeah. So there's some other questions here. Pekka wanted to know, why was Voyager 2 launched before Voyager 1?
Each Voyager had its own special trajectory. In order for Voyager 2 to be lined up in a way to go on to Uranus and Neptune, it launched first by several weeks. And then Voyager 1 went on a faster trajectory to get to flying much closer to Jupiter, and then also getting to Saturn 10 months earlier. So it's just based on the launch dates were based on the trajectories we ultimately would want them to follow.
Yeah, you have to go backwards. If you want to get to Uranus in a way that gets you to Neptune, you have to come into Uranus just this way. And to get to Uranus just that way, you have to go by Saturn just this way. And then to get to Saturn from Jupiter, you have to go by Jupiter just this way. And so that determines the launch that you use from Earth, the trajectory from Earth to Jupiter. And as it turns out, the trajectory to get onto Uranus and Neptune was a slower trajectory than the one to do Voyager 1's mission. And so Voyager 1 launched on a faster trajectory and got there before Voyager 2, even though Voyager 2 launched first.
And that was very intentional because the key focus at Saturn was to look at Titan. Yeah. And so by sending Voyager 1 first, it gave us the option, had something not worked with Voyager 1, to reprogram Voyager 2 to follow the same kind of trajectory as Voyager 1. So that was part of the thinking as well. Voyager 1, if it got all the science that it needed done at Titan, then the decision could be made to go on to Uranus and Neptune with Voyager 2.
Wow, cool. Another question Cameron Gillis is asking, are there plans for more Voyagers like Voyager 3? And what new probes are being planned to follow up with the Voyagers, if any?
Well,
Cassini.
Galileo orbited Jupiter, and so that was a follow-on of Voyager, and then Cassini orbited Saturn. Right. And so it'd be nice to take a Cassini-like orbiter, which would include a probe, to go out to Uranus and Neptune with, this whole very complex and very complete suite of instruments, along with a probe to go either into the atmosphere of one of these ice giants, or in the case of Neptune, maybe down to the surface of Triton. So there are no firm plans in place. It's something that the outer planet scientists would like to see very, very much. For future missions, there is an exciting mission. It's called Dragonfly. It's an octocopter that would actually land on the surface of Titan and fly around to different locations on Titan. Carries a very complex suite of instruments, including a mass spectrometer. There are two basically samplers, one in each of the front legs of Dragonfly, that would vacuum up, drill into the surface, vacuum up material, and do experiments on that material and look at its mass spectrum and try and see, are there any indication of astrobiology on this world, perhaps methane driven rather than water driven on Titan. So that is in the works. It's funded. Its launch date has slipped a little bit. It's probably going to get to Saturn in the mid to late 2030. So it's a ways off.
Okay. All right.
But it's taking advantage of the situation at Titan. The denser an atmosphere is and the less gravity there is, the easier it is to fly, the less power it takes to fly.
Sure.
Well, Titan's atmosphere is 4 times as dense as Earth's atmosphere, and the gravity is 1/7 of Earth's atmosphere, or of Earth's gravity. And so it's very easy to fly on Titan with a lot less power than it would take here on Earth. And so with the power from a single radioisotope power source, they can do that flying there on Titan.
Wow. Wow, that looks like that would be fantastic. After watching, the drone that they have on Mars right now, it's just it really spurs a lot of imagination of what we might do with small flying craft, on these distant worlds. There is a question about, is there still signal coming from the Voyagers? And we did touch on that earlier, but a lot of people don't know that,
Yes.
They don't know that we're, that humans are, and I think, I tell people that we're an interstellar, species at this point, because we're flying out there. So let's talk a little bit about what's going on with Voyager now, okay? And, maybe a final question, are the Voyager spacecrafts just robots, or is this human exploration because we're controlling it. So
Yeah.
I'll let you go from here.
Yeah. Well, both of the Voyagers are in what we call the very local interstellar medium. That means we're outside the heliopause, the boundary that's controlled by the solar wind that comes from the sun. And so we're making measurements of the magnetic field, the particle density. It turns out that the plasma density, the protons, electrons out there are actually greater in density by about a factor of 50 compared to as you get close to the heliopause in that region where the particles are much less dense. Some intriguing findings. The magnetic field is still lined up with the solar magnetic field. We expected it would line up with the local interstellar medium, but that hasn't happened quite yet. So we're watching for that. We're measuring the cosmic ray abundance went up once we got outside of that boundary, that shield between interstellar space and our sun. And so we're measuring the galactic cosmic rays, and they're not necessarily symmetric in how they're approaching and coming into the detectors from Voyager. So one spacecraft has 5 instruments operating and the other one has 4. And the limit on Voyager isn't the fuel, it's the power. Every year there are 4 watts less of power.
Oh.
And right now, completely running the Voyager spacecraft, including the signal to Earth, it's about 270 watts. That's all that's left. You think about that, it's less than 300 watt light bulbs,
Right.
powering the whole spacecraft. And it's about the same on Voyager 2. And it's because these radioactive power sources are decaying and also aging. And so you get a little bit less power. And so we've been slowly turning off anything redundant. We've turned off some instrument heaters, and we thought that the instruments would fail because the temperature dropped 50 degrees Celsius.
Oh, cold.
And they've never been designed or tested at those low temperatures. But it turns out the cosmic ray spectrometer and the low energy charged particle instrument, they both kept working. Their detectors didn't crack. Their electronics didn't stop working. The little stepper motor on the low energy charged particle instrument just kept stepping away. And so we're very happy. We're having to recalibrate at the colder temperatures, but what incredible engineering that those electronics.
Oh, yeah. Things were way overbuilt, I think.
Yeah, we never had any idea that. So the only heat they have left is the power, the few watts that are running the instruments now to power them and also provide the heat. And the Voyagers, with their gold records, once they no longer have enough power to function and the spacecraft essentially go quiet, go dormant, there are basically our ambassadors, our emissaries into space that perhaps someday, thousands of years from now, tens of thousands, who knows, someone might find one of the Voyager spacecraft and look at the gold record and maybe come and pay us a visit.
Those gold records, people have estimated how long will they last. And it turns out about 1 billion years.
1 billion years.
1 billion years.
Yeah.
So the way I look at it is that up until the point where the Voyagers lose power so much that they can no longer communicate with Earth and they're not active spacecraft anymore. Before that point, they've been a mission through locations, a mission going through space, looking at locations. Beyond that point, they're now a mission through time. And so they're carrying humanity, at least humanity's culture that's stored on that record through 1 billion years into the future.
Wow.
Yeah, our silent ambassadors out into space. And who knows, maybe if we get space flight and we can really make good time, maybe somebody will go out someday and take one of those Voyagers and put it in the Smithsonian or something.
Maybe on that space station. Cool.
Or on the space station, better yet. Yeah,
right. That's right. Gosh, there's so many more questions, that we could just keep going all day long. But what is on the horizon for you two? Are you looking towards retirement? Will you be involved in educational outreach for the remainder of your lives, or will you just keep working? What is it? What do you look forward to?
I think for me, I'd like to stay with the Voyager mission, and we're going to get to the point where I have to start turning off the science instruments and perhaps running into other problems with just the aging hardware, but to stick with that mission, just see how far away we get, how far out into interstellar space before those missions end. And in the meantime, I'm working on missions, thinking about ideas to go back to Enceladus. If you're going back to Saturn's moon, Enceladus, what would your spacecraft look like? What kinds of instruments would you want to take to perform those experiments, to look for evidence of life? And, you're getting free samples coming out of these geysers, and take advantage of that. And
just go scoop some up and see.
Looking at future missions. And of course, we have 9 grandchildren now, so there's a lot to watch as our grandchildren grow up and they become interested in perhaps in space and in what we do as well.
Sure.
And I've been continuing my consulting. For instance, relatively recently, I worked with a group from the Applied Physics Laboratory headed by Abigail Reimer to go back to the Neptune system with one of these orbiters to orbit Neptune and possibly put a probe onto the surface of Triton and one into the atmosphere. So I've kept that up, but I'm going to build Voyager Station. And then Linda and I are going to go up there.
That's right.
You're going.
We have a trip planned already.
Was that part of the contract that you
will be up there for the ribbon cutting?
Well, I would do free marketing for these guys, bouncing out of bed in the morning, all these things. So my mind reels at this stuff. That's wonderful. You guys have given such an incredible and very generous amount of your time with our audience today, and I really, really appreciate it. And I hope to have you back on sometime. So we look forward. You guys, Google Voyager mission, learn about it. This is still an active mission. We're learning about interstellar space now, and there's the hydrogen wall. There's all kinds of stuff. It's being followed on by New Horizons spacecraft. It's also going on a little bit later on tonight. We're going to have Caitlin Ahrens from Goddard Space Flight Center. She'll be on, and she'll be talking about the interstellar probe mission that is being developed. And so this is a nice series of talks that we've had where we've talked about the rings around other worlds, having Linda and Tom here with us to talk about that as well, and to learn about, we live in the golden age of science, exploration, and discovery. It's the golden age of astronomy as well. And so it's just, it's wonderful to be alive and to experience all this stuff. I really appreciate you guys being on.
Yeah, it was great to be here, Scott. Thanks for the invitation.
Thank you. Okay. All right. So we'll be back on at the top of the hour at about 6 p.m. Central with Cameron Gillis, who will have his program Camstronomy, where we go on the sky survey with him. And then at 7 Central, we'll have Caitlin Ahrens on in 7 months of science. So thank you very much for watching. And as my friend Jack Horkheimer always used to say, keep looking up.
Ad Astra.
Yes.
The 2 Voyager spacecraft have been traveling away from Earth for more than 33 years, and they are finally in the outer edge of the solar system. This boundary is marked by the outer reaches of the Sun's magnetic field and solar wind, which form an enormous expanse called the Heliosphere. As the solar wind travels out from the Sun, it pushes against the galactic medium and abruptly slows down. This is called the termination shock. Outside this is the heliosheath, where the solar wind slows to a stop, and the magnetic field is bent back by the ionized interstellar wind. The sun's magnetic field spins opposite directions on the north and south poles, creating a sheet where the two spins meet. This sheet gently ripples as it travels outward, and the ripples get bigger as they go. When this sheet reaches the termination shock, it starts to compress, like water waves hitting a wall. The Voyager spacecraft have now found that after the termination shock, these stacked up ripples of magnetic field form bubbles, shown here as a computer simulation. This discovery has prompted a complete revision of what the heliosheath region looks like. The smooth, streamlined look is gone, replaced with a bubbly, frothy outer layer. This new layer also changes our understanding of how extremely fast-moving particles, called cosmic rays, enter our solar system. When they arrive at the bubble region, they slowly move from bubble to bubble until they can reach smooth magnetic field lines and follow them toward the sun. The nature of the bubble region explains why Voyager 2 has been seeing variations in the number of energetic particles compared to Voyager 1. Because of its path, Voyager 2 has been passing in and out of the bubble region. When it is in the region, Voyager 2 sees many trapped cosmic rays and electrons. When it is out of the region, the spacecraft sees fewer. Even as the Voyagers answer questions about our solar system, they raise others. For example, scientists aren't clear yet how the bubbly heliosheath is linked to the ribbon feature discovered by Ibex and Cassini. This ribbon shows the emission of energetic particles and seems to indicate some interaction with interstellar space. In the meantime, the Voyager spacecraft continues sending back data, and, after 3 decades, they still have a unique perspective to offer about the universe we live in.
Add another decade.
Mm-hmm.
Oh, Goddard.